Yeah, so our goals is just to kind of identify what patterns we have like at our disposal, and how we can match against those patterns. And then another kind of big thing is just understand the difference between refutable and irrefutable patterns. It's not like it's just more something that it's good to have the back of your mind and understand what it means, because it might come up as you're compiling code, and then Rust tells you, hey, this is a refutable pattern. You have to know what that means. Okay, so patterns are like, this is like the definition from the book. Essentially, it's notes. There we go. So it's kind of a way to denote the structure of a type. So we can kind of use patterns as control flow, where depending on how we match against some patterns, we run different sections of code. So another way to think about this is kind of like a pattern is a way to define the shape of your data. So like for a matrix, for example, we always define it in terms of, is it n by n, n by p? What are the rows and columns? So they can both be matrices, but they have like different shapes. So they would be different patterns. And you can kind of have a lot of different things that fit that description. It's pretty vague. So you can have like the literal one, for example. A little bit more complex things like um, destructuring an enum or a tuple or a struct. And then we've seen match come up a lot. The pattern here is just, you could have the variable x, and like that's all the pattern is in this case. And then we've seen the underscore used in a couple different ways, but one of the ways you can do that is like a placeholder pattern for everything that I haven't told you about before. And let's see examples of all of those. So the first thing we're going to talk about is where can we use these patterns in our code? It's kind of like what are the patterns? What are some of the kind of more common cases? So we've seen the match expression a lot so far, so it should look familiar, right? We might match by some value x. In this case, it'd be an option type. So we want to check, is it none or is it some? We can't just use the value directly. But the kind of key thing I wanted to point out here is more the structure of this versus like the example. So what comes after the match is like the value you're checking against. And then inside the match is a series of pattern expression patterns, right? Or yeah. So you say like, if x matches this pattern, I want you to run this expression. If it matches the other pattern, I want you to run this other one, and so on. And another place we've seen is if let expressions, right? So if let, in this case, the pattern comes first. So if this pattern matches, if this value matches this pattern, right? So if let pattern equals value, then run this expression. And then of course we can extend it with like else if we can make this go on and kind of as long as we want. But that the same structure is still there. Pattern equals value expression. Otherwise, pattern equals value expression. So that kind of works like a match statement. But if let's more general than a match expression, because with a match we could only compare like one value, like we can only compare like one value. So we have match x, like we can't use y in one of the patterns within that expression. So with like if let, we can do that though, so we can kind of use any, almost like with any logical condition. So like the branches don't have to be like the same thing. They don't have to be related to each other. So for example, if you look at line 8 there, we're checking if it's Tuesday, right? Is Tuesday. But if we look at line 6, we're saying is some color equal favorite color. Right, so that's quite a bit different than match. We wouldn't be able to use those two patterns within the same match statement. It really makes sense. So the other main thing to know with if-let expressions is that you can have what's called like a shadow variable. So I've got a little comment there on line 11. So if we look at this, yeah. So if we look at this here, we have age, which you define up here to be as a result type. And then we say, what we're saying here is like, I want to make a new variable that shadows this value of age that we have here. So if age is okay, this is the shadow variable that I want to use. So it's not, this age here is not the same as this age. So it's kind of like when you have a function, you have like an argument called x. You could have something in your environment called x, but like within your function, it's different. So like we couldn't directly have age greater than 30 if we hadn't created this shadow variable here. Yeah, and then of course we can like nest however deep we want. Hopefully not much because it gets confusing, but like in theory, however you want to do that. Yeah, so the last thing is with the match expression, it will look at all your or look at all your patterns and make sure you have like an exhaustive list of possibilities. And if you don't, I mean, you can always use the underscore like we saw, just to say everything else. But with if-let, the compiler is not going to check that because you can use different patterns that are kind of these unrelated variables. There's no way it could check to see if everything, if you have your exhaustive list. So you just got to be more careful in these cases and make sure you're not relying on the compiler to catch that for you. So the next one is a while let. So in the structure here, so kind of pattern equals value. You have like this condition you're checking, and then if it's met, I want to run this expression. So an example of that would be like, let's say we have a vector with 3 values. We could say as long as there's some value, so while let sum top, I want to print it out, right? And so the stack.pop is just picking out the last element from the vector. But that's kind of the figure of the pattern. The pattern in this case is sum top, and then comparing that to the value, stack.pop, which will return the value that you want, and then whatever expression you want to run. Similar for a for loop, right? So we have for pattern in value. So instead of the equals, we have the in. And the kind of neat thing is you can use different kind of things. You can use different patterns here. So in the value, what we're doing is we're taking this vector v and I forget what it's called, adapting or something like that. But basically, we're getting an iterator. So you enumerate all the values in v with their index and the actual value, right? So it would be pairs of 0a, 1b, and 2c. And so for our pattern, we can say, I know enumerate is going to return this tuple with these two things. So you're kind of like creating these variables to use inside your for loop here. So it's kind of it's like destructuring the tuple that gets returned into its own, into like separate values rather than the whole tuple itself. You could have something really simple like let. So let pattern equals expression. And the expression could be anything. The pattern is like the variable name. So let x equals 5. Or again, it could be a little bit more complex where we're like destructuring a tuple and assigning each one of these variables x, y, and z. Which I really wish R had something like this because like I love it. Java 0 has stuff like this, and it has like R has dots, but you can use dots to say like everything else. Like it would be awesome to have it. We also have patterns and functions. So it's like they say the parameter is a pattern, and we can have something simple like we've seen before, right? Like say something like foo x would be the pattern, just the variable. But we could again also use something a little more complex and say I want a reference to a tuple. Excuse me. Um, that's a valid like pattern in our arguments there. All right, so that's kind of where we can use them in the general structure of patterns. But patterns don't always work the same in every place. So we have these kind of two types of general categories for patterns, called refutable and irrefutable. Um, Irrefutable just means like we're accounting for every possible value. So it's like that match. In a match where we have to say, some and none, we have to have those two branches to make sure it counts for everything. So match uses a irrefutable pattern, but we could have some that are patterns that are refutable as well. And so in different places we can use patterns, expect different types of these, either refutable or irrefutable. So we kind of got to know what they are to make sure we're using the right type of pattern in the right place. So I think to me, it's easier to think about irrefutable. You can compare irrefutable line 5 here. This is an irrefutable pattern because like the right hand side can be anything. So it's like infinite possibilities. It doesn't matter what it is. Whatever the result of that is going to get assigned to X. So it counts for everything. But this is an irrefutable pattern because um, uh, X would be like an option. Yes, option. So it could be like some or none, right? But in the pattern here, we're not accounting for the fact that we're not accounting for the none case. So it's refutable. So it doesn't match every possible pattern that value could be. And so we generally don't need to really think about these, but it kind of it can come up in the compiler, so we need to know like what they mean. And do we want to show? Oh, I forgot about that one. Yeah, so like we just saw that like this would be a refutable pattern because we're not counting for some option value can be none. So when we try to run this, Rust tells us that, hey, like you got a refutable pattern here. It's helpful because it gives more explicitly none is not covered. But then the notes here tells us let bindings require an irrefutable pattern, but like you gave me a refutable one, so I can't work with that. Yeah, and then we can fix that by essentially just using an if and say like if the value is there, then do it. If sorry, I'm looking at my notes. Yeah, so that if we don't match the pattern, like if we don't match them, then it's okay. Like we don't care about that case. And then just sure. And then so it'll run in that case. Oh yeah, I have it there. All right, so that was when we're expecting an irrefutable pattern, but we have refutable. So we're expecting to count for everything, but we're not accounting for everything. The opposite is kind of here. So if let expects a refutable pattern, because like this is always going to match. So let's see. Yeah. So what will happen is in this case, like the code will still run because we're not gonna like break anything in this case, but it's going to tell us you don't need this if here because it's not doing what you think it's doing. It's unnecessary. So the pattern will always match. So it's saying, hey, that if is that's useless. Okay. Any questions so far?
No, I think it's funny that it says it's useless.
Yeah, I know.
What
That's kind of
language
funny.
choice there.
Oh, thanks. Um, so this next section is just like like a lot of examples. So it like can be kind of overwhelming, but you don't need to know every single one. Don't remember it all. I would use this next section as like a reference to where when it comes up and you can kind of refer back to it.
Is it a mutable reference?
Immutable. Maybe they change it. Okay. Yeah. So the simplest thing we can match against is like literals. Um, right. So in this case, I mean, it's pretty straightforward. Um, we could also use uh, name variables. So this is when we want to match any value. So yeah. So it'll let us we want to match any value. We want to use it. So like we're using the sum y here. Like it's not this y. But it's just saying like whatever that value is, that as long as it matches something that it's not 50, like I want to use that. So it's not the same right here. It's that shadowing that we talked about earlier.
So would it be correct to say that like the match X is matching a refutable pattern. The Y inside the sum is actually an irrefutable pattern because the Y itself has to be an irrefutable. In this case, it's just a number, but it could be a structure or something in there, or a tuple or something in the sum
Yeah, I
case.
think so. I think that's right. It's kind of weird, kind of tricky because like this is a pattern, but like yeah, it's like everything is a pattern kind of thing.
Yeah, it's patterns all the way down.
Um, yeah, and so sometimes we want to check like more than one pattern, more than one kind of condition. So like we can do that in like a match statement, for example, with just like an or there. So if it's one or it's two, do this, and then three, and then anything else. Which I think we have something we haven't seen yet. I mean, it seems intuitive, but I guess it's not necessarily the case. So, like one kind of thing I like too is you can use like a range. You can match against a range of values. So anything from 1 to 5. I don't remember exclusive how Rust is ranges, but the idea is there. So we could also use like or, so we could use 1 or 2 or 3 or 4 or 5. But this is quite a bit simpler. I think that's the general kind of pattern with a lot of these so far. Well, the pattern is there's some kind of special syntax that makes it easier to express like more complex patterns. But this will only work for numbers, numeric values, or characters. Um, because those are the only types that Rust can tell if this range is going to be empty or not. Yeah, yeah. So you can use it for characters, for example, too. I want to look at letters A to J, or I want to see if it matches from K to Z. We saw this a few times with tuples, but you can do it with structs. So this is when you want to match different parts of the struct. So if we have a point with an X and a Y value, we can destructure the point out into like its individual components. So in this case, like take the X value and assign it to A, take the Y value, assign it to B, and then I want to use those separately. So it's kind of like you're using different parts of a composite type. So structs, enums, there's another one, but so it can be, so this is fine here, right? We're kind of giving new names here, but like if we know a point's going to have X and Y like coordinates, we probably want to use those values in our code so it's easier to kind of trace back. If we're using A down here and maybe there's a little more going on than this, it could be a little bit confusing on matching them up. So we can just say like X, Y, and then it'll give out those values X and Y. It knows like, hey, pull up this point dot X and point dot Y. Yeah, I can enums. So a little bit more specifically, we can kind of destructure enums with a match where the patterns destructure like the inner parts of the enum and use them. So I mean, this one's pretty straightforward. Quit, so message quit, like it's kind of what we've seen so far. But this move is a struct inside an enum, right? So it's kind of there's a nesting going on here. We can do like we saw before, where we can say message move, and then we can use that destructuring X, Y. It's going to pull out the X and Y values so we can use them in the expression. And similarly for like, you can have different things internal to this enum and you can destructure those all within the match, within the pattern. Um, yeah, and we can make this as complicated as you want, basically. That's kind of what this example is like. So, we have instead of just an RGB color, so in the previous one we had one of the enum things was like change color. So there'd be RGB, but what if we want HSV as well? Everything else in here is the same. But we can, let's see. Yeah, so we can kind of say, I mean, it's a similar thing, right? And they all have three values, the RGB versus the HSV, but like we can take our enum and dig into that enum within our enum. And the kind of important thing here, besides the nesting, is that these values that we're calling here, we're destructuring this enum to be able to use in this pattern. And you get like really, really crazy with this and just mix all kinds of different types and destructure them like as you need. So it's a little bit confusing, but you have this tuple here that you can say, okay, I want to give the first part is feet and the second part is inches. And I have a point over here. I want to get the X, Y, and that. And then those are both like random tuples. So have at it. Another thing we've kind of seen before that can be helpful is like ignoring a pattern. So we may not care about every case of the pattern. So we could have something like this where like I don't care what this first art what the custom is. The first one I'm just only going to use the second value. I don't know why that would necessarily be helpful unless you're doing like, I mean, I guess if you're doing like some fancy functional programming and stuff. But you could also uh yeah, okay. So I had the same thing repeated. But you can use this kind of thing when implementing a trait is like the example it gives. So your function needs to have a particular signature Like it needs to take two either two, for example, because that's how the trait's defined. But your implementation of that trait doesn't care about the first one. So I guess that's a good use case for this. You can ignore like nested values too. Like I don't care what this kind of thing is. Um, I just want to know that something is there. Like so I need to know that something is there, but like I'm not using that value in here. So instead of saying some x, some y, and then using x and y in the expression, if I don't use them there, I can just put the underscore to say just ignore it. All I care that is that this pattern is a match. I don't need the actual values to use in there.
And didn't they make a point here? Like this is not just like a matter of shorthand. It's actually is important because if you put like a variable there that you didn't use, it might move a value and cause some borrow checker issues, right? Even
Yeah, I think so.
I think they made some kind of point like that, which I thought was interesting.
Yeah, and you can kind of mix and match this. So if you want to ignore the second and the fourth element of this enum, you can just put dots there, or not dots, but the underscores, and then just pick out the ones you want to use. Um, Unused variables. We've seen this before. Um, so maybe you're like in the middle of kind of writing something, you know you're going to need this X, but like you're compiling, you don't want to see, you don't want to compiler to complain. Just put the X underscore in front of the X for now, and then do it later. Fix it later. And this is that kind of like the rest of this pattern. So if we have a point, like a 3D point, X, Y, and Z, maybe I only care about X. I can just use the kind of two dots here to say, just like, give me the X. I don't care what you do with the other ones. And you don't have to necessarily use it at the end. You can kind of use it in the middle to get the first and last values of something. So yeah, like this, right? So if I only care about the first element and the last element of this, I can just ignore all the rest. Okay, so back to match statements again. So we also have this thing called a match guard. So kind of like it gives you an extra condition to look at. It allows you to put an extra pattern in your match in the one of the patterns of your match expression. So let's just get a little bit more complex. So in the example here, this is like if you want to check if it's even, if a number is even, you of course have to count for the sum and the none cases, but you can also add this, if x mod 2 is 0, right? So with a pattern alone, we can't really like represent this with an option type because this isn't really taking care of the sum part, right? So it does let us. It's not just like a shorthand thing. It lets us do things that we can't otherwise do in patterns here. And this x here is like a shadowed variable that comes from here. So kind of like we talked before, it wouldn't be the same as an x on the outside here. We could also do things outside the match expression. So earlier we talked about like if let is a little more flexible because you don't have just the one value. We can kind of get around that with match guards. So if I'm only comparing X here, that's all I can use in these patterns here. But with the match guard, I can actually refer out to another variable as well. And like, so this reminds me kind of like list comprehension in Python. So we could have something before we have like, hey, I want to see if it's 4, 5, or 6. And I also want to check this other condition. So like 4, 5, 6, if y. It kind of looks like it, but it's not necessarily the same because y here is just like a true false. But this is that guard. So the thing to note here is it doesn't matter whether the 4, the 5, or the 6 matches. Like Rust is gonna Y has to be true for all of them. So it can't be like 4 and not Y. It has to be 4 and Y, or 5 and Y, or 6 and Y. Okay. The last thing here is they call at bindings. It's a little bit confusing. The current variable holds a value at the same time we're testing that value. Like let's see what it looks like in an example. So again, with our favorite match statement here. Okay, so we have this. We have a message that can have this enum with this variant. Hello, that's a struct with this ID. Okay, and then we'll create one of 5. What we want to match it against is we want to check the range, right? We want to see if this ID is in the range 3 to 7. Now, if down here we're doing that and like there's nothing different, this is what we've seen, right? We're destructuring that hello, or actually we're not destructuring it, but we're just saying, hey, if this ID is between a 10 and 12, do this. But we're not using the actual value that was matched. So that's what at bindings let us do. They let us, in this expression, we can use the variable that actually the value that actually matched. So it's worth like pulling up here, and I'll show you in a second. Or let's just do it now. So in this case, since ID here is 5, we're gonna get a match on this range, right? What the at expression is like, it's kind of like I want to create a temporary variable called ID variable. And since ID is 5, we're going to get 5 printed out. So yeah, like this is our ID is in the range. Here's the actual value it was. So I guess another way, the other maybe more common way you could do something like this is you would need like a for loop where maybe you have to keep an index and then indexing to get that value. It's kind of just like a shorthand to say, like, I want you to check this match and see if it's in this range, but I also want to I care about the actual value and I want to use that later. And that is all. Questions, comments? Awesome. Hey, I don't know. I was getting kind of overwhelmed putting those together, and I probably could have left some, but like I don't know how you felt it was, but I think stop. So. But yeah, it's and so I was just like, okay, I don't need to know all of these. Let's just